Next, let's look at the growth of functions. In computer science, we want to understand how quickly an algorithm can solve a problem as the size of input grows. So we can compare the efficiency of two different algorithms for solving the same problem. Therefore, we need to determine whether it is practical or to use a particular algorithm for input growth. So basically, this will need to consider the algorithm. There is a complexity or there is a cost in a time or something in a space when the input grows. So that actually has to do with something with the growth of a function. So we'll first study the growth of a function, and then we use the study to determine the growth of algorithms. In order to determine the growth of function, we will introduce some notation. The first one is called big O notation. So given two functions f and g, from the set of integers or the set of real numbers to the set of real numbers. So f and g are functions actually mapping from either from integer to real number or real number to real number. Okay, so these are very, very common functions. Then we say that fx is big O gx if there are constants c and k, that when x is greater than k, we always have the absolute value of fx is smaller or equal to the c times the absolute value of gx. Okay, so basically it's saying that if we can find two constants, c and k, such that when x is greater than this k, we always have this inequation, and then we will say that fx is of big gx. You can see that after x greater than k, the absolute value of fx is always smaller equals to c times gx. So it's dominated by the c times gx. This is read as fx is big O of gx, or g asymptotically dominates f. Here, the two constants c and k are called the witnesses to the relationship fx is big O gx. And then when you try to prove giving you any two functions g, f, and g, then you only need one pair of witnesses to prove this big O notation, big O relationship. The true meaning behind the big O notation is that we're trying to use this big O notation to say that after x is greater than this k or a certain number k, the value of fx is dominated by the absolute value of fx is dominated by the absolute value of gx. So that means the growth of the function is dominated of f is dominated by the growth of the function of g. So on the picture, you can see this illustrates the big O notation. Suppose fx and gx are both greater than 0, positive. Then originally this is your fx and this is your gx. And then if we can find a certain number k, that for x greater than k, then fx is smaller than the cgx. Because c is actually a constant. And then c times gx will not change the growth of a function. And then after the x greater than k, fx is smaller than the cgx, so which means this part. So always greater than fx. Therefore, you can see that the growth of gx is actually dominates the growth of fx. Big O notation is widely used. It will help you to understand what is the order of the growth of a function. So let's look at one example. So here, let fx equals to x squared plus 2x plus 1. Okay, so this is fx. And then if we say that gx is x squared, then try to prove that fx is of big O x squared. Okay, so x squared is actually the highest order inside this polynomial. you can see that we're trying to say that the order of the growth of the polynomial is determined by the highest order. It's dominated by the highest order. Okay, so how can we prove that? Okay, so a practical way is that you're trying to find the k and c here is that you're going to keep trying different numbers. Okay, so let's first try k equal to 1. So when x is greater than 1, it's easy to find out that x is smaller than x squared, right? When the value is greater than 1, the value x is also always smaller than x squared, right? It's very, very common. And also x squared is greater than 1 too. So with that, we can easily see that 0 is smaller or equals to, this is fx, and smaller or equal to, because x squared is equal to x squared, right? 2x is, because of this here, x smaller than x squared, so 2x smaller than 2x squared, right? So 2x smaller or equal to 2x squared. And also we know that 1 is smaller than x squared, so 1 is smaller than x squared. So these three plus together is smaller or equal to these three plus together. And then, so on the right hand side is equal to 4x squared. So you can consider this is your gx, and this is your c, 4 equal to c. So then you get a witness, pair of witnesses. So we can take c equal to 4 and k equal to 1 as the witnesses to show that fx is big O x squared. So that proves fx is big O x squared, right? And another interesting fact is that the c and k might not be unique. You can find some other pairs, multiple pairs, as long as you can prove the absolute value of fx is smaller or equal to the absolute value of gx. That's by the definition. So let's try different c and k. Okay. So for example, if we say, let's say try k equal to 2. So let's see what happens when x is greater than 2. Then we will have you can easily find out that 2x smaller equal to x squared, right? And then also 1 is still smaller than x squared. And then go back to the function. The 0 is smaller equal to fx, smaller equal to x squared. Okay, x squared smaller equal to x squared. 2x smaller equal to x squared. And 1 is still smaller than x squared. So this is this 3 plus smaller equal to these 3 plus together. And on the right hand side is equal to 3x squared. So in this case, if your k equal to 2, then you can choose c equal to 3. Okay, so because of the inequation. So you can see using two pairs of c and k, we can easily prove that fx, which is a polynomial, is a big O of x squared, which is the highest order of the polynomial. And we can see that the polynomial, the growth of polynomial is actually smaller, is dominated by the highest order of the element. On the picture, you can see here this function is x squared, and there is a function here. This is fx. This is polynomial. And if we times 4 to x squared, that becomes this one. And you can see after x is greater than 1, the fx is smaller equals to the 4x squared. And if x is greater than 2, also you can also use square 2, then the fx is smaller than 3x squared, okay, as we already proved. So you can see this part will already show that using c equal to 1, k equal to 1, c equal to 4, we already proved that fx is big O x squared. Okay. In general, given any polynomial, fx equals to an xn plus an minus 1 x to the n minus 1 until plus a1x plus a0, where these parameters a0, an are real numbers with the highest order one, an not equal to 0, and x greater than 1. And then in general, we say that the fx is big O xn, x to the n. So how to prove this? It's very easy. Let's first look at the absolute value of fx, which is equal to the right-hand side. And using the triangle inequality, okay, the triangle inequality is no matter what is a and b, a plus b is always smaller or equal to the absolute value of a plus b, always smaller or equal to the absolute value of a plus the absolute value of b. And then here, using same here, for the fx's absolute value is smaller or equal to the absolute value for the plus of absolute value for each element. Okay. And then we move all these together, put a x in, x to the n out, and then look at the parameters. So we have an, and then an minus 1 divided by x, and then a0 divided by x and to the n. And then because here x is greater than 1, so this part, for each one of them, it is less, for each one of them, it is less equal to the parameter itself. Okay. For example, this one is smaller than equal than 1. And this is smaller equal than 1. This is smaller equal than 1. So you can just say this smaller equal to the xn times the absolute value, the sum of the absolute value of each parameter, an to a0. And then we can see that we already found the weakness is that we let k equal to 1 and let c equal to the plus of the sum of all these absolute value of the an plus absolute value of an minus 1 into absolute value of a0. This is your c, and then we can see that fx absolute value smaller equals to the c times xn. Okay, so you can see we already proved that fx is big O xn. So that means the linear term, or the highest order of the term of the polynomial, dominates its growth, so which is very, very useful. Let's look at some common functions, growth of functions. First of all is number 1. Number 1 is representing a constant number. For example, 1, 2, 3, these are all constant functions. So there's no growth for these constant functions. The next one grows a little bit faster is logarithmic function, log n. And then log n, which is like a linear function, grows faster than log n. And next one is n log n, is faster than n. And then next one is n squared. And next one is 2 to the n, which is exponential. And the fastest one is the factorial, which is very, very fast. Another notation, similar with big O notation, is called big omega. The only difference is the big O notation means that fx is smaller equals to the gx. But in big omega notation is fx is greater equals to the c gx. So then we say that after you find the same c and k, then we say fx is big omega of gx. So big O actually gives you a upper bound of the growth of function. And big omega, because of definition, gives you a lower bound. So that means that the fx is always greater than equal to the growth of the gx. So that's the meaning for big omega. So fx is, the relation between the big O notation and big omega notation is if fx is a big omega gx, if and only if gx is big O notation, big O fx. This is very easy to prove, okay, according to their definition. Let's look at one example. For example, fx equal to 8 x to the third plus 5 x squared plus 7 is big omega gx. Here gx equal to x squared. Okay? So that means that the growth of this function is at least as fast as x squared. Okay? So here is very easy to understand, because when x, no matter what value is actually given to x, this part is always greater than 0, right? So the fx is always greater than 8 times x cubic, right? So then we prove the big omega. Very easy. You can also use the definition to prove that gx squared is big O of the fx. Using the big O and big theta, we can define another notation. It's called big O and big omega. We can define another notation called big theta notation, which is very, very simple. So the function fx is called big theta gx if fx is both big O of gx and big omega of gx. Okay? So we say that f is big theta of gx, or fx is of order of gx. Or you can say fx and gx are of the same order. So that means the growth of fx and the growth of gx, these two functions, are actually same order. So the growth very, very in the same order. Okay. And then to prove that, you can find prove fx is big theta gx. You can find the three pairs, C1, C2, and K, such that C1 gx smaller equal to smaller than if fx smaller than C2 gx if x greater than k. Okay. This follows from the definition of big O and big omega notations. And based on the previous examples, we can see that we can prove that for any polynomial fx, a n x to the n plus a n minus 1 x to n plus n minus 1 plus a1x plus a0, where the parameters a0 to an are real numbers with an not equal to 0, is actually of order xn, or big theta xn. So that means the order of any polynomial is the same as its leading term. This proof is an exercise. You can try to prove that after class. So for example, very easy, for fx equal to 8 x to the 5, 5x squared plus 10 is actually the order of x to the 5. And for the next example, this one polynomial is order of the leading term x to the 199. So, how to prove a big theta notation? Okay, so first of all, if fx is big theta of gx, then also gx is big theta of fx. And also, if fx and gx is same order, then you can actually prove that first of all, fx is big O of gx, gx is also big O of fx. Okay, and in our computer science algorithm, you look at some books. So most of the time, people are using big O notation rather than big theta notation. Okay, so that means actually is to give you an upper bound, and sometimes it could be even if the algorithm complexity, the growth of the algorithm is the same as the notation inside the big O notation, but we still use the big O notation. Okay, so it's just like a habit when people use the complexity, and most of the time we just using big O notation to give you upper bound, even though it could be the same order.